Great, thanks everyone. So yeah, I want to bring us into more of this observational space to answer the question that I know a lot of you have and always the students ask, which is, well, how do we really know that, right? How do we know what we think we know? And I want to show you kind of what some of those observations look like, what we're looking at in the data when we say this is a star being disrupted by a black hole. And I'll talk a little bit about some of the research I'm doing, kind of connecting these back to the galaxies that host these supermassive black holes. And at the end, I want to show you an activity that I've been working on to try to teach students a little bit about how we take the data, use our mental models, and how we can go about trying to find, these events in real time and how that, kind of how some of that scientific intuition works. The files for that, I think, I've sent to Maggie. I think you have access to maybe like a Google Drive with those. Awesome. If you have any questions about the activity or any of that, my email is up here, deckerkf@illinois.edu. I'm also, I think, the only Decker French in astronomy, so that name helps. And I should say, I'm happy to answer questions throughout. If you've got questions, raise your hands and we can do mics as we go. I'm plugged into this. I'm not. Maybe I can. Perfect. So I want to talk about two main ways of finding these events, and I'll focus on some current work and also some future work. We've heard a little bit about the Vera Rubin Observatory, which is going to really revolutionize our ability to find and discover these events. One of the reasons that we're having this conference now is because this this rising tide, as the title says, of these events is coming soon. Really, in the next year, we'll start to get this really sea change in our ability to do this kind of measurement. And the idea for finding these events is to do an experiment that in astronomy is actually very, very old. We want to look at some object in space and see, does it change? Look for new things. People have been doing this, as long as people have been looking up at the sky, right? Early supernova, we have records that supernova were found by eye. People thought, wow, that's pretty intense. They wrote it down, and we have records from thousands of years ago, right, of people seeing supernova, actually that now we can, date and see, oh, now we see the remnant, we can find that. And you can do this by eye, and certainly even relatively modern supernova in the past few decades have been found by eye. People saw them. Most of the time, what we're doing now, though, is entirely computer-based. So the idea is this. You have some image of a piece of the sky that we call a template. This is sort of what we think was happening when nothing was around. And then if we take a new image, we can subtract off our template and look for any new stuff. So this is some real data, and this is most of what we see, where you subtract off your old image, and assuming everything's gone correctly, there's nothing there. There's nothing in this image that's very exciting. This is one of those things that is easy to explain, but actually a little bit harder in practice to do, right? Where when we're thinking about these tidal disruption events especially, they're happening in the centers of galaxies. So, if there was a supernova over here in kind of the outskirts of this galaxy, that would be pretty easy to pick out. We're really trying to pick this out of the noise of the center of the galaxy, though, and that adds some difficulty. And from the background, you can kind of see where we might get led astray. These kind of dark and bright spots, if we were trying to say, is there anything new, anything different in the image? We're trying to kind of rule out some of these, and we have a number of ways of doing that with statistics, now a lot with machine learning, but ultimately we're just trying to find something new. And here's an example where we did see something, but also illustrate some of the difficulties of our data, where this is the new image, this is the old image, and by eye, this is really hard to tell. Really, we need to do the subtraction, look at the difference image to see, yeah, there's something new and bright there, right kind of in those crosshairs. And you can see actually in this case, what we're doing is we're just taking these images which are on CCDs. And what we have is an array of multiple CCDs. You can only make them so big off the shelf. And this gap here, this isn't something I put on the slide. This is a gap in between our detectors. Had we gotten a little bit more unlucky, this would have been just in the detector gap and missed in this observation. And that sort of thing happens, all the time. And so, we take our new image, we subtract off the old image, and we detect something new in this case. So I'd said this method is extremely old, right? And this is how we found a number of things in astronomy. This kind of thing where you look for something new in the difference is how you find any number of things. So we mentioned supernova, which are orders of magnitude more common than these tidal disruption events. But this is also how we can find asteroids, how we found Pluto. Pluto was found in exactly this sort of thing. They weren't using CCDs, right? They were using plates. You can do the same sort of exercise with old photometric plates. There's a machine at Carnegie, which is where Brenna is now, that, or you can see this, where it's, you put in 2 plates, and you can actually blink between the image and look for differences kind of by eye. And if you have really good eyesight, better than mine, you can detect these small differences. And people have been looking for these for a long time. This sort of thing now with CCDs and machine learning, all of that stuff, is how we're characterizing all of the nearby asteroids that might be hazardous to Earth, really trying to keep track of what's out there. And what might be coming through in this is that this kind of science, right, where you want to look at as many galaxies as you can, look for all these differences, is really complementary to the kind of data that a lot of other scientists need. So for all of these observational efforts to find TDEs, we could do it ourselves if we could convince, say, NASA, that finding stars being disrupted by black holes was more important than defending the Earth from nearby asteroids. That's going to be a little bit of a heavy lift. Really, this is a place where collaborative efforts have been helpful across all fields. So the same kind of data that works for these tidal disruption events works for a number of these communities, for asteroids, for supernova, for variable stars, things like that. Yeah, question?
Since data is such a, since data is so important, old image and new imaging and looking, are we using more AI? Or are we, using that to do this? And in reference to getting outreach, are we using citizen science? Because it's something I know they do, maybe not this level, but having people come in to help to see the difference.
Absolutely, yeah. So machine learning is super important in this sort of thing because what we can do is something like this is pretty clear by eye what it is, and we have lots of data that has been trained by people looking at it, and that's exactly what we need for training machine learning AI models to say, here's a bunch of kind of labeled data sets where we have, here's the truth, and you can kind of train the system and say, okay, now in some new data, guess, is this real? Is this an artifact? Right, like this thing here, this is an artifact. These little spots are artifacts. This is real. And machine learning is really, really good at that. A lot of that is to the point where we, like what I'm showing here is kind of a small snapshot of around a galaxy. But if we're trying to do this at a scale where we have this for most of the sky is 40,000 square degrees. That's a lot of this. For perspective, this next generation camera on Rubin Observatory, the scale of it blows my mind, and this analogy helps put it in perspective. To look at it on a 4K TV, a single kind of frame of this, you have to tile a basketball court with 4K TVs. That's a ton of data, and that's just one field, and we're just going to do that every 30 seconds, all night, every night. It's a ton of data. And so one of the key things that machine learning does now is takes us from just totally unfathomable amounts of data to a small set that we can kind of do some final human vetting. The goal is to make as much of that final human vetting not even needed for many of these sources as well. Because to do human vetting, you need someone to be awake and clicking on stuff after this is done. And if you have a really fast kind of event, if your event happens in minutes or hours, you want that to be automatic. You want this to be downloaded, analyzed, with a signal sent to another telescope to go follow something up. And there's a ton of progress being done on that. A lot of the people here at Santa Barbara and Las Cumbres Observatory are working on that sort of thing. You mentioned the citizen science. There's also, I think, there's part of a family of things called Galaxies, which probably a lot of you are really familiar with, and the kind of the Zooniverse projects I believe one of those is trying to classify these light curves as well, but I'm less familiar with that. But yeah, we can chat more later.
When you're using this data and I'm so sorry. When you're using this data and you have this AI or this language going here, are there, you know how you program your bias within it so that sometimes you miss something that you really should not have placed in there? How do you back that up? I mean, what are the procedures that you do so that does not happen, that you really can discover something?
Yeah, so we try to do as many tests as we can to like inject fake sources and see how well do we recover those. There's a lot of concern, especially for something like this chip gap, right? This is just going to be random. Occasionally we'll miss stuff because of stuff like this, or something that happened like just there on the edge we miss. Gaps in time between observations are a lot harder to overcome. We have a huge bias towards events that are really long in time, that last for months or years, versus events that live for many hours. We're probably missing a lot of those. So for example, Brenda showed this great plot of how bright something is versus time for the small black holes and large black holes. And you might imagine that we're much better at finding things around those slightly larger black holes than the slightly smaller black holes. And we have to model all of that and correct for all of that to say, if we measure this number of black holes versus mass, that must mean that the real kind of underlying distribution is this other thing that we can model. I don't know if that answers some or all of your question, yeah. So this is the kind of thing that we're doing. So I want to show you kind of what this looks like now as a function of time. What this is showing is actually a really famous event. During the conference, we took a poll and had a runoff of everyone's favorite tidal disruption events. And one of them, called Assassin 14 Li, which is named after a survey called Assassin, was found in 2014. It got to the runoff phase. I voted for it. I like this one. AT 2019 QIZ on Friday afternoon, someone showed some really cool results from this, and so it ran away with it, this one won. But Assassin 14 Li is a very nearby, really well-studied event, and this is how it was discovered. So this is a series of images, where this one up here is the reference image of the galaxy. Assassin has an interesting trade-off where these pixels are kind of large, but that doesn't mean that the data is bad. That means actually that the amount of sensitivity you have in any pixel is actually really good. And what's being shown here is now a case in 2014, June 21, the difference, the subtraction. This is now the template minus the new event. And what you see here is a big, beautiful thing of nothing. It means that the system is working, even in a galaxy. There's nothing here. June 24th, nothing here, nothing here, nothing here, nothing here, nothing here, nothing here. Between here and here, there's a big gap where the object was too close to the sun, between July of 2014 and now November of 2014. But here you can almost start to see there's like a black spot there. This is sort of the opposite map of what we saw before. And then here, you can start to see, oh, now there's like an actual source that their method deemed was significant. And we can start to say, all right, something here was detected. We detected some kind of event. So this is what we're trying to do really on a really large scale. This sort of experiment where if this is right around a galaxy, we'd like to do this over as much of the sky as we can. And we have some trade-offs, right? The more of the sky that we look at, the less we can observe any individual patch of the sky. So for example, if we wanted to maybe find this earlier, find it when it was fainter, if it was rising, we might have to observe for longer. And so that's just a trade-off if you have a finite amount of time and a finite size telescope. We have this trade-off between how deep do you observe, how often do you observe, and how much of the sky do you observe. So I'm working on a project at the University of Illinois with a number of other collaborators. This is called the Young Supernova Experiment, and the name probably tells you that the only reason that I'm doing this is because some of my supernova friends are doing a lot of science as well. And what we're doing is this. So we're using the two Pan-STARRS telescopes, which are on Haleakala and Maui. And what we're doing is not mapping the entire sky. We're trying to map as much of the sky as we can that maximizes our chances of finding Well, we'll say supernova because of who most of the survey is, but that also means we want to look at galaxies. This is our map of the fields that we look at. And so what's being shown here is this right ascension declination, a really odd map of the sky that's missing the main feature in it that we've been looking at, which is the galaxy, which we don't want to look at. We don't care about that. This is young supernova experiment. It's not young variable stars and galaxy stuff experiment. So we mostly don't want to look anywhere near the galaxy because of the dust in it. And these circles are kind of targeted based on where we have a lot of galaxies, a lot of archival data that's useful. And we're looking at as many of these fields as we can, basically every 3 nights, to pretty good depths. And what we do then is we make these plots now with data that look like what you saw from Brenna earlier, where we look at the flux that we receive in those little detections as a function of time. And you can see that they kind of rise and they fall. Sometimes the fall-offs look like that lovely 10 to the minus 5/3 power law. Sometimes there's some variability. And in general, these rise and fall over months kind of time scales. And where then we really need to get more information, and where the activity I'll talk about later comes into play, is how do we know that this sort of thing is actually a star being disrupted by a black hole? This is only part of the information that we need. So in the activity, I'll show how, when we look at these kind of light curves, it actually looks really nice when you can see the whole thing after the fact, right? You can see this thing, you say, all right, that's some kind of light curve. But what if you wanted data during the event? What if you had to know here whether this is something interesting or not, right? And you only had this amount of data. That's where it gets a little bit more challenging. So the next piece of information we need, once we have one of these detections, is to try to see what it is. With these TDEs, we do want them to be in the centers of galaxies. It's an important clue. But there's a lot of stars in the centers of galaxies too. So what we really need is a spectrum. So this is a set of 2 spectra from that event that I showed you, Assassin 14 Li. So we're taking that light, dividing it up into wavelengths, and this yellow spectrum is a spectrum that was taken in 2007. There was no TDE at the time. There was no flare. This is actually just the underlying galaxy, the light that we're seeing. But then in December of 2014, about a month after that discovery, you can see that the spectrum looks very, very different. This is saying that what's being shown here is the galaxy plus this new thing that we have. And so we can see that there's this broad emission line. This is H alpha. There's a number of other interesting broad lines. There's this overall blue continuum. This is that black body emission that we saw earlier, where what we're seeing is about a 30,000 Kelvin black body, which, again, too cool to be accretion, but is maybe the reprocessed accretion or shocks. We've had a lot of discussion at the conference on exactly what causes all of these interesting emission mechanisms. And so we can get some evidence of kind of what was disrupted and also what the structure of the ionization is around the black hole. And really do science with this, as well as say that this thing is actually very, very different than a lot of our other flares like supernova and things like that. And now that we've been doing this kind of science for a while, we've started to see a lot of similarities and also some differences between these events. There's now something like 100 well-studied tidal disruption events. And you can see kind of a little rogue gallery of what their spectra look like. This is a recent work by Yuhan Yao, who's also at this conference. And we can start to do science not with like 1 or 2 individual objects, but really groups of these. We can constrain their rates. The rate is about 1 per 10,000 or 100,000 years per galaxy. And so really in your survey, if you want to find many of these, you need to have tens or hundreds of thousands of galaxies in your survey. And this sets kind of the parameters of what you would need for, well, how wide should our survey be? How faint should we look for? How often do we need to go back and look at what we have? And so really the reason for this conference is this big slope change in the number of TDEs per year that we can look at. So until about 2019 or so, what's very recent, we were in this regime of having about 2 new TDEs per year. That was very exciting to look at them individually. We could do some statistics. We were learning about what they were, how to identify them. And in the past few years, we've been in this really exciting regime where we have now dozens of them every year. It's not like a groundbreaking thing to find a new one. It's a groundbreaking thing to find a weird one, to find how they fit together. And all this is going to look very cute in a few years. Next year, the Rubin Observatory's legacy survey of space and time is going to turn on and should find thousands of TDEs per year. And really, there's a lot of exciting science that we'll be able to do with this, and some exciting challenges in dealing with this amount of data. Because this is, when I say that we'll be able to find 4,000 TDEs per year, that's not quite the right statement. The right statement is photons from thousands of TDEs per year will reach the detector of LSST. And to find those in the data is going to be a real challenge. And the amount of data that we were able to collect for some of these really cool, well-studied events will not be possible for thousands of events per year. And so this is why this is happening. So this is the Rubin Observatory. It is kind of a just massively scaled up version of those experiments that I showed you before, where normally we have a telescope like this, 8-meter diameter, that is looking at a handful of individual PI's programs. Rubin is really more like a physics experiment, like you hear about with the CERN or something like that, where basically all of the time on this telescope is running a survey of the entire sky accessible from the southern hemisphere, where it is in Chile, and it's going to scan the sky in multiple colors every few nights over the course of its 10-year survey. And they have some cool renders of how that works. And this is really a step up in every direction that matters in that trade-off. We have a huge field, right, that basketball court full of 4K TVs. It is going to look at very faint things. This mirror is much, much larger, and the amount of light we can collect scales as the area of the mirror, not just the diameter, so that d squared is giving us a lot more sensitivity. And it is able to just handle a massive amount of data. Right? It's able to scan the sky much faster than what you would have been able to do with kind of a big telescope with less time. It has that huge field of view that you saw. This big thing with all the colors in it are the different filters that we'll be able to put in to see kind of a mini spectra of how much blue light versus red light we have. And it has this really interesting mirror design to help us look at a very wide area on the sky. So I want to kind of switch gears now and show you this activity. Oops, if I can do this. That we put together to try to teach some of the skills behind this. And so the idea for this activity is that if we're trying to understand what things are from these light curves, from looking at how bright something is as a function of time, when we're trying to do this either after the fact or in real time, that involves a lot of the skills that I know are important as part of Common Core and things like that for using mathematical thinking, developing and using models to try to say, if I know what kind of a class of these things look like, how can I generalize that to something new? Trying to convince your peers from evidence from the data of what something is, how to communicate that and express some confidence or some uncertainty in what something might be. And so the idea is this. So there's a set of documents that go with this. And the idea is to start out by putting students in groups where each one has a case study of a specific kind of event that has a different variation as a function of time. So there's a set of these little documents that explain some of the physics behind what these events are. There's active black holes, there's variable stars, there's supernovae, and there's an example light curve of what these look like. And the goal is to have students kind of break out and do these, and then in their small groups, teach the others to kind of say, I'm the expert in supernova, here's what we should look for in this activity, here's what supernova are, why we see them. And one of the students is an expert in observations and light curves for understanding these plots and what they are. And so the first part of this is kind of the case studies, which could be either kind of a small group, kind of 30-minute thing. I thought we maybe just had enough time to not quite be able to do this in the hour. Otherwise, I would have had us do this. Or this could be a homework or something like that. And then the actual activity is this. This is, sorry, just a copy and paste of the activity. But the idea is, and let me go back to my screen sharing, to do this, to show a bunch of light curves and have the students try to guess in real time what they are. And the goal is to make this a competition to, one, get people into it, but also to penalize wrong guesses. Let me explain. So not to be mean, but the idea is to do this. So this is kind of the slides for it. So to start, the idea is you could look at an entire light curve. So this, the instruction notes have the correct answer in them. So this is a Cepheid variable star, which looks similar but a little bit different to the one in the example for the student who gets variable stars. And this is super clear, right? You could put this in and kind of pattern match and say, well, this looks most like Joe's thing, and go from there. There's a complete supernova light curve here, which, yeah, seeing the whole thing, you can say, all right, that rises and falls. And this is the kind of thing that, you know, we do need to do with surveys. People do this kind of thing. But if you wanted to know what the spectrum was here versus here versus here, which is how we get a lot of information about these sources, you have to know to look at it early on. And so some of the challenge then is to start from this, start from how we actually get the data. We get the data once every few days, right? If we're observing once every few days, we get a new data point once every few days. It's happening to us in real time. And so the idea is to start with this, and then, if this will let me do this here. And in the document, there's a few ways that you could do this like automatically with some set time. But the idea would be to start to go through and have students say, if you guess this right and you're the first team, you get 2 points. If you guess first and you're wrong, I guess you could be nice and give them 0 points, or you can give them negative points. Because in real life, if you say, I'm certain this is Cepheid variable, and it's not, the community, you know, loses some trust in your method, right? And you kind of go from there, and you can see, all right, kind of went down, all right, kind of keeps going down, and you can see there's a lot of observations. You know, at what point do you become confident or not of what it is? There's a question, I think. No. And so there's a few of these. And the idea is, depending on how, you know, that went, you know, students want to change anything about their strategy, they're meant to be, really would step through these kind of slow enough with like a minute, you know, or so between them to have people say, all right, what do you think it is? Someone said, well, it's going down. Does that mean maybe it's one of these? What ones have like a decline in them? Maybe we missed the rise and it's just the decline. Those are the kind of things that you would want them to be kind of talking about in their groups, right? That's where they're making the model. They're taking what they know, they're applying the model to this. They're trying to use the data to convince one another that that's what it is. They're trying to convince their own group that maybe they have some rapport with from talking about the case studies. They're trying to convince the other groups as well that, yeah, we're first and we're right. And they're all different. At this point, they might say, well, it keeps going down. It rises. And here it looks like the Cepheid person is probably like, oh man, that looks like really like mine. But maybe the supernova people have given up. And yeah. And so you can see, and so there's a few of these skipping through really fast, but this next one is weird and more variable. And then you can ask kind of what worked well to identify the objects, what didn't work, things like that. So I think this sort of thing can be a useful way to kind of show maybe more conceptually, you know, when you look at these light curves, right? to kind of put in perspective like that this is a human timescale, that we are trying to apply models to these, and that kind of our models might change if we're doing it in real time versus if we're trying to do this all after the fact. Let's see, questions before I start? Yeah.
Just wondering what does really distinguish a supernova light curve from a TDE light curve?
Yeah, what distinguishes a supernova?
Scales are similar.
They are, yeah, and there is a reason that I didn't put TDEs in that activity with a supernova. I had planned on it, and then I thought, it's too mean. And the answer is, would depend on who you ask at this conference. There's a few people who have a method to do this, and basically what you need is a little bit more than this. And people will disagree with me on this. This can be confused with a supernova. It is bluer, and it's more constantly blue. And so really what you want is more of that color information, which you can get even with 2 filters. And I thought introducing filters was maybe too much complexity for this. And I should say, for this activity, please use it. Please let me know how it goes. If you look at it and you say, that wouldn't work in my classroom because of this, or man, this would be good except for this thing, I'm super open to feedback and editing the thing. So please let me know either way, maybe especially with critical comments, so I can make this better. For the TDEs, you still have a lot of, we think about this in like purity and completeness, right? Of like how pure is your sample, how many contaminants you have, and how many are you missing because of the method. And in selecting things that are blue and look like this, you get still a lot of contaminants. A lot of the methods that are working really, really well use machine learning because you can pick out kind of these subtleties that by eye or by like a fit model are kind of difficult. So there's a few groups that are using machine learning models, not just for identifying TDEs, but also for identifying all of these things. And that has been working pretty well. And really like gearing up for LSST, this is one of the big tests of how well will our kind of algorithms for classifying things without all the spectra work.
Have you considered in that activity starting with the actual images rather than the light curves?
Ooh, that's a good idea. Yeah, have I thought about in the activity starting with the images? And let me show you, I think I put this in. So each of these are the case studies. And in the observations one, I have some of these. So the person who worked on the observations has some of these images to kind of learn how do you go from observations to light curves. And so my goal is that they take kind of this printed out or on like a screen and can kind of show this to the other students.
I meant actually like the students have the images and they do the measure.
Oh, I see.
Using like,
yeah.
There's like JS9, which is like some
Yeah.
kind of astronomy software.
I haven't, but that's a good idea. Yeah.
Yeah, where they can like actually just make the curves themselves.
Yeah, a lot of, I think, let's see. I have an example of this that could be turned into something students could use as like a Jupyter notebook. I'm not sure how much people use Jupyter notebooks at like at the level that they teach, but that is often a really good way. And astronomy has a set of astronomy tools called AstroPi, and it has something to kind of get the light curve out of this. Yeah, that's a good idea. Okay. Let's see, other questions.
This slide that you had, the years past, present, and 2025.
Yeah.
Is that because, of course, one is the telescope, two, technology, and understanding how to make a distinction from the pattern? Is that why we expect 4,000 in that period of time?
Yeah, mostly the technology. Mostly, like we've had the technology for this, the basics of this for a while. There's certainly things that are very new, especially dealing with like the volume of data and things like that. This telescope is, its own kind of bespoke, custom-built thing that required a lot of technology. But I think it's just a matter of resources at this kind of problem. We've never had a telescope this large with this much of its time devoted to doing this kind of survey. And I think some of it is, the technology, the cheapness of detectors has been key. A lot of these surveys are using telescopes are not new, but say the cameras are very new. And it's much, much cheaper to, say, have a really big camera than it would have been, in sort of these early days. But yeah, also what to look for, and to show that we can do interesting science with this kind of data is key. To just have developed all of the different tools in all of these different communities for, say, asteroid detection. In the supernova community, they are super interested in like the type 1A supernova that uses standard candles, things like that, to show how much better we can constrain technology with this amount of data and things like that. So I think it's a combination of mostly resources kind of put at the problem, as well as the tools.
Hello. Okay, I have 2 questions. So you mentioned that the data shows that the TDEs rise and fall over a months-long time. And is that because of the radius of like how fast some stars are moving and everything, or do we know why, or why?
Yeah, so that time scale works out to be about that orbital time scale for what kind of like a typical supermassive black hole mass is for the stars that are close enough to be tidally disrupted. It's also a very convenient time scale for us to observe and for where we see a lot of galaxies that have supermassive black holes. If the supermassive black hole is too massive, then we don't see the TDE, and those would be longer. And then for the very kind of lower mass black holes, it might happen over hours for a very small black hole, and we haven't been able to detect that on quite the same scale.
Nice. That leads into my next question, which was with this newer technology and just having more telescope time on the sky, do you expect patterns to change?
Yeah, absolutely. I talked about like the main part of Rubin, which is going to be kind of telling the whole sky on these kind of 3-day time scales, looking at a different color every time, and little sets of these. But there are these fields that they're calling deep drilling fields that they're going to look at more often. And as we get this sort of like higher cadence, we call it, data, we're going to find new classes of things for sure. I think the list we could write down of what we think is going to be interesting with LSST is going to be different than what people say what was actually the most interesting in 10 years. There's an absolute ton of work that goes into trying to predict as much as possible what we see from these kind of things, like for JBC, for this, for Hubble. But looking back on 30 years of Hubble, like I think what we think is most interesting is not what people thought was going to be most interesting when they proposed to do that mission. So I'm always excited about the serendipitous stuff that we don't expect.
I want to take it inward. I know we're looking outside of, I want to take it inward. I'd like to know, are we going to be looking at our own galaxy, was in our own backyard, just as much as everything else? And did we already look at everything? I mean, is there anything else to learn?
Oh, absolutely. There's a ton of stuff to learn still in our own galaxy. Most of my expertise is in these like extragalactic things. That's what I've been focusing more on. But there's a lot of really cool science you can do also in the time domain looking at our own galaxy. A lot of what we know about variable stars is mostly stars in our own galaxy. And stars that are variable, like some of the light curves that I showed, are variable for really physically interesting reasons. In that sometimes you get the entire star like physically pulsating, like changing radius, changing luminosity on these rapid time scales, which is very different physics than the physics of our sun, right? Our sun, it freaks people out when like there's an eclipse and it gets dark over the course of minutes, right? Like the whole planet goes to like a narrow region that goes through southern Illinois. To have the sun change in luminosity and in radius, like yikes, right? On these time scales is just so far beyond what we think about for solar physics. It's just a different regime of what we can learn. And we've been looking at variable stars as a community for years and years, but there's a lot of things you can do with exponentially larger samples. There's also some cool stuff you can do with what we call gravitational microlensing, where you get little bits of, like I was listening to GR stuff that we heard about from Eric, little bits of kind of lensing that we get from stars passing in front of other stars. We can learn about some of the non-luminous matter. If dark matter was a bunch of like free-floating planets, we probably would have seen it already. But to constrain the amount of that is something we can still do. We find planets this way. That's all super interesting. And yeah, we're in a really cool time as far as Milky Way studies for this, but also from a survey that you've probably heard about called Gaia, which has been getting really accurate distances via parallaxes, and also velocities via proper motions and redshift. That's mapping out kind of that 6-dimensional 3 in position, 3 in velocity phase space of the galaxy. And we're finding some stuff that you think, we've looked at the Milky Way for 100 years, right? And with astronomy, right, we've already known the stuff. Oh, the Milky Way had a huge thing, not that big of a galaxy, but a huge thing come in and merge with it, and we can see kind of the pattern of that splash of the stars still in these orbits. There's a lot of really cool stuff that people are doing there. So yeah, Milky Way science, less represented in, I think, this group of scientists, but really, really cool.
Have we observed tidal disruptions with solar mass black stars? Something like black holes?
Yeah, we observed tidal disruptions with solar mass black holes. I think this answer somewhat depends on maybe who you ask at the conference. I would say not yet, but there are some interesting candidates for things that might be this sort of thing, especially in smaller mass black holes and like globular clusters. There's some super cool candidates for these that I would say like interesting, but we should find them in more real time. And you can see like from the light curve, you can say, oh, wow, that could have been that thing. But if we had a spectrum early on, right, and maybe the spectrum looked different. And yeah, I think the answer is maybe for all the lack of assignment that answer is, yeah.
Hi, thank you for all the work you did in connecting your research to the classroom. I think we all appreciate that. I had one question and then one suggestion. When the students do the activity, is there a goal just to get it right? Like, do they say, I got it, and then they move on?
The goal is to get it right and to get it right first.
Okay. So my suggestion is that what students will tend to do is they'll go, is it this? And then they, no, it's not. Then they go, is it this? No, it's not. So it might be better, just as a suggestion, to have them justify their reasoning behind it.
Yeah.
Otherwise, they'll just guess their way through it.
Yeah, so I like the idea of the justifications, and I think each group will get like a guess. So if they get it and it's right in their first, they'll get like 2 points. But if they guess wrong, then they lose the ability to get points, and they can't.
And then my second comment was, did you mention that you know the people that collected that data?
Yeah, yeah.
Okay. So I would suggest putting a biography of those people, because I just think it's really important for the students to hear the stories of the people behind the people that are collecting the data.
That's good. Yeah, I like that. Yeah. All right, so in, I think, our last few minutes, let me show briefly some of this other stuff. So one of the things that I've been looking at lately is really, now that we have a collection of these events that's more than a few, we can start to ask some of these meta questions. And we talked earlier about some of the motivation about the coevolution of galaxies and black holes. And my expertise in coming at this is not general relativity, it's not stars, it's actually galaxies. And so this was sort of the question that got me into this field, which is, all right, so if we can use these to trace black holes, well, what kind of galaxies are we looking at? And this is really found on kind of that first order, just what are we looking at when we look at the kinds of galaxies that host these? And when we ask what kinds of galaxies, really what we're looking at, if we're looking at it in optical light, is what kind of stars in the galaxies host these events. I know since a lot of people teach intro astronomy and looked at this are familiar with like HR diagrams and spectral classes of stars. And basically, if we take stars and group them in order from in terms of temperature, from these bright blue stars to these fainter redder stars, we can say that these are quite hot and also luminous, and these are cooler. And the different patterns here, what these are spectra, just colored to show what the wavelength is, and these dark lines are absorption features in the atmospheres of those stars, with all the light that's coming out from fusion kind of propagating through those cooler atmospheres. And exactly what lines we get tells us about the temperature of those envelopes. It tells us what elements are basically available to absorb some of this light. And generally, we have these kind of blue stars and these red stars. And when we then look at galaxies, we can kind of say, all right, when we see these blue galaxies, basically what we're seeing is, if I made kind of these bar charts of the amount of light from each type of star, this kind of galaxy, it still has all of these blue stars. And so we know that because those don't live as long as the red kind of cool stars, this galaxy must be continuously kind of replenishing that supply of the blue short-lived stars. And then this galaxy over here that looks mostly red, when we kind of add up all the light, is missing all of these stars. So they probably died off a while ago. And it just has these stars that live a long time. These redder stars live, more than 10 billion years. And so if they formed at any time, they're probably still around. And this gives us this idea that galaxies evolve from something like this to something like this. Hubble had this backwards. Hubble thought that things got more complex over time. And to some extent, that's true, but they don't get bluer over time. And we think that these galaxies evolve into these. And so what is really useful is that we can do more than just kind of blue color and red color. We can use the fact that these lines here that kind of start out faint and get darker and then go faint again are really characteristic of these intermediate age stars. And so by looking at the spectra of galaxies, we can kind of say to a much more kind of fine level in time what the ages of galaxies are. And so we can identify galaxies kind of in the middle of these star-forming galaxies to the galaxies that are long dead, and say that these are caught in the middle. We've caught them just so that these ones have died out and these ones are there. And this is a long way around of saying we knew some of this stuff about galaxy ages before all of this. A lot of this stuff was developed in the 70s by Beatrice Tinsley. And so just thinking about this from a galaxy's perspective, we can say, all right, I'm going to make a plot. I'm going to say, how much current star formation do we have? And I'm going to look just at the strengths of those intermediate lines, which trace our kind of intermediate galaxy population. So these are star forming. These are those long, kind of dead. And this is where we see those more transitional galaxies. When we look at where we find the galaxies that are hosting these tidal disruptive events, there's way more than we should expect by random chance in this area with the transitional galaxies. And this tells us something super interesting about the fact that stars coming close to the black hole are not just random. If it just didn't matter what the host galaxy was at all, they'd be kind of some here and a bunch here. There's way too many here. And that tells us that there's something kind of connecting these really large scale trends we see with what the stars are doing, with what's happening at the tiny kind of inner parsec or so for what stars are going into the black hole. This is a topic of why that's the case. It's something that we talked a bunch about at this meeting, and I think we'll continue to talk about. And we have maybe a good situation for physics and astronomy. We have too many explanations for probably what it is. Always good, so we can try to pick between them. It's probably multiple. But a lot of the work that we've been doing in this field looking at these transitional galaxies is to try to understand, well, why do galaxies go from this to this in the first place? And the major mergers of galaxies is probably key there, where if you merge two of these together, you get a bunch of things that do affect what happens at the centers. Really excitingly, you have two black holes. You have one black hole in these galaxies that will eventually merge. You have a lot of gas in both galaxies. When the galaxies collide, that gas gets funneled to the center. The stars in the galaxies can basically pass right through each other. They're basically never collide. The gas won't. The gas will collide, forms a whole bunch of stars. You get a starburst. Maybe the velocities of the stars are very strange, more likely to cross the center. We have a lot of interesting things to test. So with that, I think I'm almost out of time. So I'm just going to leave up this cool simulation. If you want to visualize what happens when the galaxies collide, that I think suggests that we do have a lot of reasons why we should get a lot of stars being messed up into orbits in the centers somewhere in the end of this process. So with that, I will answer more questions. And yeah, I put my email up on that first slide. Happy to talk more after this as well. So thanks, everybody.
All right, thanks, Dicker, for taking us in a more observational direction. We have time for a few questions before the coffee break. So maybe starting up here.
So a lot of my students talk about Andromeda being on a collision course with us. Have we mapped out a simulation that would kind of show the demise of sorts?
Yeah, exactly. Yeah. So we have a number of these simulations that are either kind of a zoom like this, where it's two galaxies and they just merge. We've also have simulations that are trying to be over a volume that has, many thousands, tens of thousands of galaxies, that has a bunch of these mergers. To measure exactly what happens for the Milky Way and Andromeda, one of our main uncertainties is exactly what the Milky Way is doing. It seems like it goes back and forth every few years of actually which one is more massive. I think right now Andromeda is winning. I think the Milky Way is actually like a satellite of Andromeda now. But we have a lot of uncertainties about our Milky Way in setting those initial conditions. But we do have some simulations that show kind of what we should expect as far as that both of them are gas rich, and we should get something that looks a lot like that scenario.
Okay.
So with the 80 black holes that we have in our own system, do we anticipate collisions with that?
Oh yeah, so most of the black holes that we have the best evidence for, that we know about in our own galaxy, we know about because they're in binary systems with other stars. So there's the ones that are bright in the X-ray, where the X-ray is coming from the fact that they're so close to another star that it's not tidally disrupting, but it is tidally interacting. And some of the mass from that star is kind of feeding an accretion disk around the black hole. And so those will eventually merge and collide, but on probably too long of timescales to be interesting to us. And then the ones that were in the news recently are also in binary orbits, which helps us kind of constrain the mass, like the total mass of the system and this reduced mass quantity. And the good thing about them being in binaries is that it gives us a lot of observables. The downside is that those binaries are probably too stable to interact. And so that kind of leaves a third thing needing to come in and interact with them. And especially for the stellar mass black holes, that's a really small target in space. And so if we think about the total distribution of where stars are, what their velocities are, we can say, what is the rate at which we should find one of these? And it's really, really low for our Milky Way. So I think our Milky Way is pretty safe from one of these. It's disappointing to the astronomers, probably good for our desire to not be irradiated by gamma rays and stuff like that. If one of them has a jet, I guess you're the expert on how many have jets.
I should say your question reminded me. I promised you I would go look up how many stellar mass black holes there are in the Milky Way over lunch. And the number is uncertain because most of them aren't producing light that we can see. But according to NASA, there may be something like 100 million of them out there somewhere in the galaxy, which is still a very small fraction of the, compared to the total number of stars in the galaxy. But it's quite a large number. So you really get a sense from comparing 80 to 100 million or 10 million that you have to get very special conditions before we can see them. But yes, so yeah, it's pretty rare for jets to be produced, and I think we're going to hear a lot more about jets and all of that fun stuff after the coffee break. I think we have time for maybe one or two more questions back there.
I'm going to double check first. Does anybody on Zoom want to unmute and ask a question?
So for the known black holes in the Milky Way, using the Gaia data, are there any stars headed towards those black holes that would produce TDEs?
So I think the rate is still pretty low. They would have to be extremely close. So for scale, if you picture that the video that we saw of the stars kind of orbiting around our Milky Way's black hole, that closest one is on an orbit that we just looked at this. It was like 20 years.
Yeah, it's like 10 or 20 years.
Yeah, 10 or 20 years. Compare that to the orbital timescale for something that could be disrupted being like, months, right? It's a really, really small target to hit. So most things won't hit it. As far as predicting from the stars around it, I think we don't have the full information that we need because most of the stars are going to be too faint to do that. So for the more massive stars, we can say, okay, this one probably won't, this one probably won't. But there's a lot of stars that are then too faint to be included in that catalog. That will be kind of the majority of the possibilities. There'll be a boring small star that's less massive than our sun by statistics.
I think then we will go off to coffee break, and Decker will be hanging around. So if you have more questions, feel free to find her then. See you all in half an hour.